This video discusses conic sections in the polar coordinate system. This is based on section 7.5 out of the OpenStax Calculus book, Volume 2. In this section, we take a brief look at how to represent different conic sections in polar coordinates. We have already studied conic sections in our college algebra class and also in Calculus 1. So we'll just briefly review that here. However, we want to take a longer look at how to represent a conic section in the polar coordinate system. The reason is that because they are based on curved shapes rather than shapes based on line segments, as what you get in a rectangular coordinate system, the polar coordinate system is ideal for representing conic sections such as circles, ellipses, hyperbolas, and parabolas. Before we do that, though, let's briefly review what you've learned in college algebra or pre-calculus and in Calculus 1 about conic sections. We'll start with the definition of what a conic section is. Many people wonder, how did a conic section even get its name? Why do we call them conic sections, since parabolas and circles and ellipses don't look like cones? The reason is because they do come from something that is cone-shaped. So what we call a cone is actually a single nap of a cone. We think of a cone as being like a party hat or a witch's hat or a dunce's cap. In fact, a cone has two identical parts, both the upper and the lower. The hourglass is in fact a cone, although we would think of it as two cones, one on top of the other. Each of the conical parts is called a nap, spelled N-A-P-P-E. One of the naps is what we tend to think of as a cone, but in mathematics, of course, technically the cone has two naps, which means that it is a double napped cone. When you're looking at this, we call it a right circular cone because the base of each cone is, of course, a circle. And the right comes from the fact that if you put a line through the center of the circle and through the point where the two naps meet, that it would be at a right angle to the base, which is the circle itself. In other words, the height of a single nap is perpendicular to the base of the nap, and that's what we mean by the word right. It's at a right angle. And we'll continue to refer to as a single nap as a cone, though technically the cone is both naps, because I know that it will be hard to avoid years and years of practice at calling one of these a cone every time you want some ice cream. Now, how do you get this? Basically, what you do is you take a line that goes through the origin and you rotate it around the y-axis. This line that you see here is the line y equal 3x. Now, you may not be really clear on where exactly that line is, so let me outline the line for you in red. The line is the line that goes along the edge of the cone and lays along the side of the cone. If you were to take this line and spin it in a circle about the y-axis, you would generate both naps of the cone. Now, let's take a look at some more information that we've already learned about cones. One of the things that we know is that we can get different shapes by intersecting the cone with a line or a plane. If we think about the line itself formed by coming down the edges of the cone, then we know that a line is technically a conic section. Again, because the line can lay along the edge, the line is technically a conic section. Also, we can consider a point to be technically a conic section, since the point where the two naps meet is considered a point. So a point's also a conic section. Typically, though, when we talk about a conic section, we're not talking about points or lines. What we're talking about are shapes that curve in a two-dimensional space. We're talking about a circle, an ellipse, a parabola, and a hyperbola. Now, I'm going to show you some pictures in real life of what these look like because it is very difficult to visualize from a two-dimensional picture what you're actually getting. But what you see here in the picture are what are called conic sections. Again, the word section comes from the fact that we are cutting the cone in different ways. Let's start with the circle. The circle is cut parallel to the base, which is, of course, itself a circle. When you cut parallel to the base, all of your cross sections will be circle. Let me show you on a real model what that will look like. You may have seen a model like this before. This is a single nap of a cone. And when you pull it apart into various pieces, we can demonstrate what a conic section means. In this picture here on the right, you'll see that the cone has been cut parallel straight across to the base. And what you get, of course, is a perfect circle that you can see here in the picture. That's what the circle is. Let's take a look at the next conic section, which would be an ellipse. You'll notice here that this, what looks like a piece of paper, but we can visualize as a guillotine, cutting through the cone, you can see it's in an angle. It's not parallel to the base that the bottom nap is sitting on. It's at an angle. When you do that and you look down from above, you'll see that what you get in the result is an ellipse. This gives you a perfect ellipse in that cut. And the cross section depends on the angle at which you cut it will determine how long the ellipse is and how narrow the ellipse is. Let's take a look at a different conic section. The parabola and the hyperbola are different from the circle and the ellipse in that on the parabola, you'll see that while it is cutting through one side of the cone, it's not cutting across the other side. Both the circle and the ellipse cut through both sides of the circle completely. In the parabola, however, and the hyperbola, it only cuts through one edge of each nap. Parabola only cuts through one of the naps, but the hyperbola cuts through both naps. There's more to a parabola and a hyperbola, however. Let's take a look down here at the real-world pictures of a parabola. You'll see here that this is the cone model consisting of different pieces of wood that have been fitted together to demonstrate. You'll see also off to the left side that there's a board here. Now, the board is leaning up against the parabola, or rather not the parabola, up against the single nap that we have here. Can you see in the picture that the angle at which the board is touching the cone, or the single nap of the cone, is in fact parallel to the angle of the cut that produces the parabola? In other words, this red line and this red line are parallel to each other. When you cut through one nap of a cone parallel to the edge, in other words, to the line that produced that cone, you will get a perfect parabola, as you can see here in the cross section. Let me outline the parabola for you now. There is the parabola right there. And again, this is made by cutting through one nap at the same angle as the line that produced that cone. Now, that will give you the parabola. What then will give you a hyperbola? In this picture of a hyperbola, you'll see that the cut here was made vertically. It's not required that it be vertical. However, what is required to get a hyperbola is that you have to cut at an angle steeper than the line that produced the cone. If you don't make it steeper than this, then you won't be able to cut through both naps of the cone because you'll miss the other one. In other words, the parabola, since it's at an angle that is parallel to the line that produced it, parallel to this, will never again intersect the other nap. If you make the cut steeper, then you should intersect both naps of the cone, and that's what produces the hyperbola. The hyperbola does look parabolic when you just see the one piece. This is only half of the hyperbola. The other half, of course, would be up above it because we would have to have the other part of the cone extending above. And that would give us another part of the hyperbola above it. Let's now talk about some other things we've learned as we've studied parabolas, circles, ellipses, and hyperbolas as conic sections in college algebra and calculus 1. We'll start with the parabola since it is probably the simplest of the conic section shapes. When you're thinking about a parabola as a conic section, and not as the one that you learned first in college algebra or algebra 2 in high school, remember that the conic section view of a parabola is that there is a focal point, which we usually will indicate with the uppercase letter F, and there is a line called the directrix, and halfway between that focal point and that line is the vertex. And when I say halfway, I mean precisely halfway. The distance between the focal point and the vertex and the line is often written with either A or P, depending upon the textbook. In this particular one, you'll see that they're using P to represent the distance between the focus and the vertex and the directrix. That means the distance from the focal point to the directrix is, of course, 2 times P. Now, of course, when we think about a parabola, remember that a parabola is basically the set of all points that are the same distance from the directrix as they are from the focus. In other words, these two line segments here are identically the same length. That's the definition of a parabola as a conic section. The set of all points equidistant from a fixed point in space, aka the focus point, and a fixed line in space, aka the directrix. Again, you can look at your parabolas whether they're opening up or down or left or right, and you can locate where the focus point and where the directrix is with a little bit of information. As a conic section, we can look at them in this particular format. Now, this is the format that your textbook is using. Y equals 1 over 4p times x minus h quantity squared plus k. I prefer a slightly different form. Let me write those for you now. In the two forms that I've written here, you'll see that what I've done is isolated the binomial that's being squared. I can do that whether I'm talking about a parabola that is a function, where it is the x binomial that is being squared, or a parabola that is not a function, where it is the y binomial that is being squared. In both cases, the point HK is the vertex. Also, in both cases, P is the distance between the vertex and the focal point and the vertex and the directrix. The sign of P tells you whether it opens up or down, left or right. As you might expect, if P is positive and it's a function, it opens up. If P is negative and it's a function, it opens down. If it's not a function, meaning it opens to the left or right, and P is positive, it opens to the right in the positive direction. And if P is negative, it opens to the left, which is the negative direction. Here are two pictures which show the parabolas opening to the right and the parabola opening to the left. Notice that the focus is always inside the arms. I like to say that the parabola hugs the focal point. In other words, it's its focus, so it hugs it. Whereas the directrix is on the back of the parabola. It's curved away from the directrix line. You also learned about circles as well in college algebra and in Calculus 1, but we've done those enough and I'm not going to bore you with that here. I just want to cover the parts I think you may have forgotten. So let's talk about an ellipse. When you're looking at an ellipse, there are major points you need to think about. There's the center, which is not actually on the ellipse. The center, of course, is here. Normally, I would use an X for the center since it's not on the ellipse itself. We also have the endpoints of what are called the major and minor axes. The major axis is the longest one. The minor axis is the short one, whether it opens horizontally or whether it is vertical. Now, we typically let lowercase letter a represent half the length of the major axis. So a is always longer than b for an ellipse. b is half the length of the minor axis. c is the distance from the center to the focal points. There are two focal points in an ellipse. The plural of that is foci. There are also two directrix lines. You can think of this as being sort of like two parabolas put together, though the curvature for an ellipse is different than the curvature for a parabola. But it makes sense that in both cases, the focal point would again be inside the arms, and that the directrix lines would again be on the back of the curve, which is precisely where they're located. You'll also see in this picture here on the right-hand side that we have another relationship, which is that the distance from the center out to the directrix line is given by a squared divided by c. You're going to want to remember that or write it down somewhere because that's coming back for us later on. Now, when we look at this relationship here, you'll see that they're using a lowercase letter e, which is also italicized. This e is not Euler's number. This represents eccentricity. The eccentricity is a measure of how curvy the graph is. When we talk about eccentricity, we take the ratio of two different distances, and that becomes the measure of eccentricity for all the conic sections. The distances that we take are the distance from any point on the conic section to the closest focal point, and from the same point to the closest directrix line. Looking at the picture, they took point P here. The closest focal point is at F1. They take the distance between P and F1 and divide by the distance from the same point P straight at a right angle to the closest directrix line, which is L1. You'll notice when you look at the picture and when you look at this point here, that it does appear that the distance between any point and the closest focus point is always smaller than the distance between the point and the directrix, and that is the case for an ellipse. In other words, the distance of the eccentricities is going to be less than 1 for an ellipse. Here are the different equations that we can use to represent an ellipse depending on whether it is horizontally oriented or vertically oriented. Remember that the center is always HK. In this case, since it's vertical, the major axis is vertical and the minor is horizontal. That means that to move along the minor axis, we will add b to the h coordinate and subtract b. To get to the endpoints of the major axis, we will add k to the or add a rather, to the k value, which is the y-coordinate of the center. When we're looking at the horizontal, we have the opposite situation. HK is again the center, here represented by 3, -1. To get from the center to the endpoints of the major axis, since it is now oriented horizontally, we need to take h, which is 3, and add and subtract the a value, which here is 5. That will put us at 8 and at -2. To reach the endpoints of the minor axis, you will come to the center again, and since it's oriented horizontally, we'll take the k value, -1, and add and subtract 2. That puts us at 1 and at -3. When we studied hyperbolas, we also knew that the center was an important point and that it did have a major axis and a minor axis. The minor axis doesn't actually show in the hyperbola itself, but it's needed in order to draw it. The major axis is called the transverse axis. When we draw it, notice that if it is opening horizontally, that means to the right and to the left, that our axes here, the a value goes from the center to the vertex on each branch of the hyperbola, and that a in the hyperbola may not be longer than b, like it is for the ellipse. For the hyperbola, the one that determines whether it opens left, right, or up, down is the term that is positive. Whether the denominator is larger in absolute value or smaller does not matter. It's the positive one. When we look at it, you can still get to the different points from adding to the h coordinate the value of a, which will take you to the left and to the right. Now, what about when you add b to the k? It doesn't produce any point that is actually on the hyperbola. What it does do is let you draw a rectangle, and this rectangle will give you the asymptotes that the hyperbola's arms will skirt along. When you draw the box and you put the diagonals with dashed lines through it, the hyperbola will hug along these dashed lines as they go out forever and ever towards positive and negative infinity. The same is true on the hyperbola that is opening up and down. Now, where would you expect to find the focal points? Again, inside the hug of the arms, and that's precisely where they are. Again, C does represent the distance from the center to the focal point. But unlike on the ellipse, where C was necessarily smaller than A, on the hyperbola it's reversed. C is longer than A. So on the ellipse, A is longer, but on the hyperbola, C is longer. Now, where would you expect to find the directrix lines? Remember that on the ellipse, they are on the back of the curving part, just as it is for a parabola. If we apply the same logic then to the hyperbola, I would expect the directrix lines to be here in the center, between the major vertices, and in fact, that is where they are. In this picture, in the right and left opening hyperbola, you can see that the directrix lines are in fact between the major vertices and on either side of the center, which is here. You'll notice also that the eccentricity represents the same thing. It's the distance from a point on the hyperbola to the closest focal point divided by the distance from the same point to the closest directrix line at a right angle. However, in a reverse situation to the ellipse, On the hyperbola, the distance from the point to the focal point is longer than the distance from the point to the directrix line. That means that the eccentricity for a hyperbola is greater than 1. Ellipse eccentricity is less than 1, hyperbola greater than 1. Returning to our graph of the sideways parabolas then, what would the eccentricity here be? Remember what our definition for a parabola was. It's the set of all points that are equidistant from the fixed point in space, the focus, and the fixed line in space, the directrix. In other words, the eccentricity for a parabola must be 1. I'll use a lowercase cursive e to represent eccentricity so you won't confuse it with Euler's number, which is about 2.718. This means that the eccentricity for a parabola must be precisely 1, since the distance to the focus and the distance to the directrix are the same. Let's talk for a moment about what would make an ellipse become more circular. Well, if I could sort of squeeze the sides in, then the focal points would have to come closer to the center. In point of fact, a circle is an ellipse where the two focal points coincide at the center. In other words, the focal points are at the center. Now, in that case, what's happening to the directrix lines? As the focal points get closer together, the directrix lines get further away. So as the focal point's distance from the center C goes to 0, the distance that the directrix lines are from the center goes to infinity. On a circle, the focal points are at the center and the directrix lines are at positive infinity and negative infinity. Here's a picture that will help you keep in mind the relationship between the eccentricities of the different conic sections that we'll study. When you have a circle, remember that the focal points have coincided with the center, so C is 0. That means that in that case, the eccentricity is going to 0. Now you may say, but that's not quite right, because it's supposed to be from a point on the curve to the focal point. And for a circle, that would be, of course, the radius. And you're correct. But remember that when you're looking at an eccentricity, it's not just the point to the focus, it's the point to the focus divided by the point to the directrix lines. And the directrix lines for a circle have gone to positive and negative infinity. Therefore, when we're looking at a circle, what I have for the eccentricity is the radius, which is a constant, divided by positive or negative infinity in absolute values. We know that that, of course, goes to 0. That's why the eccentricity of a circle is 0. The eccentricity of the parabola is 1 because the distance from the focus to the point and from the point to the directrix are the same. On the ellipse, it is closer to get to the focus from a point on the ellipse than it is to get to the directrix lines. On the hyperbola, it's the reverse. You can see here with the relationships in the numbers and the different shapes how the eccentricity is affected. Here is the same relationship in words. Again, I'll use a slightly different symbol, though technically we do use lowercase italicized letter E to represent both Euler's number and eccentricity. We also have this relationship for eccentricity, that it is the relationship between C over A. This is true for all the conic sections. Do you remember the A squared over C I told you to remember earlier? Notice here that it is on both the ellipse graph and the hyperbola graph. A squared over c is the distance from the center out to the directrix line. Now, if the center is not centered at the origin, then you can't write the equation of the directrix line directly with a squared divided by c. In this case, if this were hk, then the directrix line would be h plus a squared over c, and there is another one to the left at h minus a squared over c. The same thing is true over here on the hyperbola. However, the distance between the center and the directrix line is always the magnitude of a squared divided by c. A is the distance from the center to the edge on an ellipse, the major axis. It is the distance from the center of a hyperbola to the vertex on the hyperbola. When you're looking at the parabola, however, we just think of this as simply being a distance of a, or you may want to call it p instead. And again, it is the same on either side of the vertex. You'll be happy to know that we are not going to relearn all of that information. What we really want to know is, how does a polar coordinate system make it easier to work with these conic sections? If you'll remember from college algebra and calculus 1, the equations for the ellipse and the hyperbola are quite complicated, especially when you want to look for the directrix lines and the asymptote lines. We want to see if using polar coordinates could make our job simpler, since polar coordinates are, of course, based on circles, and circles curve, as do hyperbolas, parabolas, and ellipses. In order to do that, we need the concept of what's called a focal parameter. We'll use a lowercase letter p to represent the focal parameter, p for parameter. This is not necessarily standard, though it's certainly not unusual. There are other textbooks that use different letters for this. I kind of like the p for parameter, however. This will be the distance from a focus point to the closest directrix line. We don't have anything that represents this thus far. Remember, in the previous picture, what we did discover is that a squared divided by c is from the center to the directrix lines, but we didn't have a distance from the focal point to the directrix line. That is now going to be represented by the focal parameter p. In this table, you'll see the focal parameter for the three primary different conic sections that we look at: the ellipse, the parabola, and the hyperbola. We could, of course, also list the circle. In this case, remember that A is half the length of the major axis of an ellipse. For a hyperbola, it is the distance from the center of the hyperbola to the vertex on one of the opening arms. On a parabola, however, A represents the distance from the vertex to the focus point, or from the vertex to the directrix point, since it is the same distance. Now, when you look at these, notice that we do have the eccentricities listed. For an ellipse, it is less than 1. For a hyperbola, it is greater than 1. For the parabola, it is 1. And of course, for the circle, it would be 0. When you're looking at these, notice the focal parameter. This is again the distance from the focus point to the directrix. On a parabola, it should be 2a. Remember what the picture of the parabola looks like. This distance, which we've marked here as p, is from the directrix to the vertex, and then from the vertex to the focus point. That makes the distance from the focus down to the directrix 2p, or on the table 2a. You'll also see here two different equations which are very similar and yet not the same for the ellipse and for the hyperbola. For an ellipse, the focal parameter is a squared minus c squared divided by c. For the hyperbola, it's c squared minus a squared divided by c. They're both divided by c. The question is, which one is which one? It's pretty easy if you think of it this way. On an ellipse, a is larger than c, so it must be a squared minus c squared. But on the hyperbola, the focal point is further away from the center, so c is larger than a, so it must be c squared minus a squared. No, I don't expect you to have these memorized. Again, this is something that you would be allowed to put on a formula sheet. By using this focal parameter P and the eccentricity lowercase letter e of the conic section, we can derive the equation for any conic section in the polar coordinate system. We'll assume that one of the focus points for an ellipse or a hyperbola, or the single focus point for a parabola, is located at the pole. This will make our equation finding much simpler. Yes, it is possible to have them not at the pole, but we won't be looking at those this semester. Again, this means because we've put the focal point at the pole, that in fact the center of the conic section is almost certainly not at the pole, unless of course it's a circle. The circle is the only conic section where the center and the focal point coincide. In that case, then we would have the center providing both the focal point and the center at the same location. Let's take a look at how we can use just the focal parameter P and the eccentricity E to derive the equation for any conic section in polar coordinates. Here are the equations for conic sections in the polar coordinate systems. R equals the eccentricity E times that focal parameter divided by 1 plus or minus the eccentricity E times cosine theta, or R, the radius, equal to eccentricity E times the focal parameter P divided by 1 plus or minus the eccentricity E times sine of theta. That's it. That's all you can have for a conic section. This equation here will represent a parabola or an ellipse or a circle or a hyperbola all in one fell swoop. For us, we simply need to remember which one's which. Again, eccentricity of 1, got to be a parabola. Eccentricity of 0, well, that's got to be a circle. Eccentricity less than 1, got to be an ellipse. Eccentricity greater than 1 must be a hyperbola. From there, we'll need to know, does it open and have its major axis horizontal or vertical? If cosine is in the equation instead of sine, then the major axis is horizontal. On the other hand, if sine is in the equation, the major axis is vertical. This should make sense to you since cosine is x, which controls horizontal, and sine is y, which controls vertical. Getting the conic section in the correct polar form and graphing it is not terribly difficult, but it can be a little bit tricky. First off, you've got to make the constant term in the denominator be equal to 1. Again, the equation must have a positive 1 as that constant term. So what do you do when it's not 1? Well, simple. You multiply by 1 in the form of the reciprocal of whatever the constant is. If it's negative 1, we'll just multiply by a negative 1 divided by negative 1, which is, of course, still 1. However, we'll remove the negative from the 1 in the denominator. That will then allow us to write 1 plus or minus the trig function. Once you have that constant term in the denominator equal to 1, then we focus on the coefficient of sine or cosine. This is the eccentricity, the absolute value of that coefficient. That will identify what type of conic section you have, according to the rules we've already talked about. The next 4 rules here are really one rule in disguise. I've written them as 4, but really it's all the same concept. Once we have the constant as a 1, and we've examined the eccentricity, and we know what kind of conic section we have, then we can look at the numerator, which is the product of the eccentricity and the focal parameter, which is p, so that we can determine what the focal parameter is. Now keep in mind that when you're looking at the equation, the plus or minus sign is not a part of the eccentricity. Eccentricity is considered a strictly positive value, unless it is 0 for a circle. If we're looking then at the focal parameter, then it is the one that is carrying the positive or negative of whatever is in the numerator. That means the focal parameter could be positive or negative. If it is positive and the denominator has a positive sign, then the directrix line will have a relationship to the pole in the positive directions, above or to the right. Above, if it is a sign-related graph, meaning that it's vertically oriented, or to the right, if it is a cosine-related graph, meaning that it is horizontally oriented. What if the focal parameter is positive, but the denominator has a subtraction sign? Then I've got one positive and one negative, so as you might expect, the location of the directrix line will be in the negative directions, to the left or below the pole. It will be below the pole if it is a sign-related graph, meaning vertically oriented, and it will be to the left of the pole if it is a cosine-related graph. What if the denominator has a positive sign, but it is instead the focal parameter that is negative? Doesn't matter. One positive, one negative, it will be in the negative direction. Below the pole, if it is sign related, or to the left of the pole, if it is cosine related. Well, what if we have both a negative focal parameter and a subtraction in the denominator? Our favorite situation in math, where a double negative does make a positive. In that case, it will be located in the positive direction, above the pole for a vertically oriented sign-related graph, and to the right of the pole for a horizontally oriented cosine-related graph. Let's run through some quick examples and see how to apply what we've learned to different equations. In example 1, we're to put the conic section equation into the correct polar form for graphing, then sketch the conic section by hand. We'll check our results on a graphing calculator or a Desmos. Probably we'll use Desmos. The graphing calculator in this case doesn't buy us any advantage because I don't need to know what the orientation is or what the angles are to get it graphed. I simply want to know what the entire conic section looks like after it's graphed. And for that, Desmos is a good tool. Here is the equation for the conic section. R equals the ratio of -1 divided by the quantity 1 plus cosine of theta. Up here to the right, I've added in the 2 different equations that serve to represent all the conic sections in the polar coordinate system. Do you remember what step 1 was? Step 1 is get a 1. Step 1, gotta be 1. Looking at the denominator, we do have a positive 1. In that case, I know that I'm ready to get started. Once this is a 1, then I look at the coefficient of the trig function in the denominator. I ignore the plus or minus sign and think of it in terms of absolute value. Whatever that coefficient's absolute value is, that is the eccentricity. There is no number written here in front of cosine. That means that the eccentricity on this problem must be equal to 1. If the eccentricity is 1, then I know that this must be a parabola. Once I know it's a parabola, then I can focus on the numerator. Notice that we are starting in the denominator, working from left to right, and then hooking around to the numerator. I've identified the eccentricity is 1. Once I know that, I'll be able to find the focal parameter P, the distance from the focus point to the directrix. Now I can find P by saying that the eccentricity times P is equal to -1. But the eccentricity is 1, which means that the focal parameter must be -1. Now, since P is negative, but I have a positive sign in the denominator, then I know that the directrix line will be either below the pole or to the left of the pole. Then I look to see whether I have sine or cosine. I have cosine, which is controlling x and horizontal motion. Therefore, the directrix must be to the left of the pole. The focal point I'm interested in is at the pole. Let's draw a sketch. To help in producing the graph, I've reproduced here the image of the polar coordinate system superimposed on the rectangular coordinate system, which is in the background, the squares. Now, remember that when we're graphing our conic sections, we're always going to put one of the focal points at the pole. The directrix line we're talking about is the one closest to that focal point. That means that right here at the pole, I have that focal point. I can use an uppercase letter F to represent the focal point. Now I know that the distance from the focal point to the directrix line is 1 because the focal parameter is -1. Again, because the focal parameter was negative, but I had a positive in the denominator, I know that it should be located in the negative direction, and because it's cosine, that means to the left. That means that the directrix line must be to the left. Where would it be located? Well, it's got to be a distance of 1 away, which on this graph is pretty close into the center. Let's make the graph larger so that we can look at it and make it a little bit smaller. The focal point is here, but the directrix line has to be 1 away, which is here. But I know that in fact, the directrix line has to be to the left, which means that the directrix line has to be going this way. If the directrix line is going this way, and I know that it's oriented horizontally, that must mean, because it's a parabola, that in fact the vertex is halfway between the focus and the directrix, or right there. Now, once I know this, I could then start to draw the parabola. The parabola's arms must be opening off to the right. It is a sideways opening, a right opening parabola. To get a better idea of where the parabola is going to show up, I need at least one more point on the parabola. The easiest value to compute here would either be when theta is equal to 0 or when theta is pi over 2. When theta is pi over 2, cosine of pi over 2 becomes, of course, 0, and this gives me that the radius is -1. Where would that be located? If I'm looking at it, remember that pi over 2 would travel up away from the pole. However, a radius of -1 would shoot it out along the 180-degree line towards 3 pi over 2. That means it goes through that point. However, don't worry, if I use 3 pi over 2, I again get 0, and the radius is -1, which would normally go down towards 3 pi over 2, But since it's a negative radius, it shoots me out towards, you got it, pi over 2. And that would be there. In other words, here is my parabola. Let's take a look now at one graph that was produced on Desmos and see how close we got. Now, if you wanted to produce a better graph, you could, of course, calculate what it is at some of the different angles that you see here. I would recommend for this equation pi divided by 3, since I know that the cosine of pi divided by 3 is 1/2. 1 plus a half would be 3/2, which would seem to say it's at negative 2/3. Let's take a look now at what we have. Here's the graph produced by Desmos. You'll see that the vertex is indeed right here along the negative line towards pi, and that it is at 1/2. See also that it is intersecting the 180-degree line between pi over 2 and 3 pi over 2 at 1, just as our estimate did here on this circle. Let's try another example. Here's example 2. Our equation this time is r equals the ratio between 8 and the quantity 2 minus sine theta. This time, our constant is not already a 1. The first thing we have to do is fix that 2. It doesn't do any good to fix anything else because it will mess up the 1 that you get here later. Always start with the constant in the denominator. Since it's a 2, I'm going to multiply by 1 over 2 over 1 over 2, since that's just equal to 1. That gives me in the numerator 8 divided by 2, and in the denominator I need to distribute the 1/2 over each term. That gives me 1 minus 1/2 sine of theta. I can then rewrite this as 4 divided by 1 minus 1/2 sine of theta. Now that I have the 1, I can find the eccentricity. Remember that when we look for eccentricity, we do not consider the sign to be a part of it. The eccentricity is the absolute value of the coefficient of the trig function after you have made the constant term in the denominator a 1. That means that my eccentricity is 1/2. Since that is less than 1, it must be an ellipse. Now I can find the focal parameter from the numerator. Remember from our equations up here that the numerator always represents the product of the eccentricity with the focal parameter. EP then must be equal to 4. However, I know that E is 1/2. Since E is 1/2, then what does that make the focal parameter P? Multiplying both sides of the equation by 2, I get that the focal parameter P must be equal to 8. The 8 is a positive number. However, in the denominator, in the correct form, I have a negative. That means this is negative and this is positive, so it will be located, the directrix line will be located in a negative direction with respect to the pole. Because I have sine in the denominator, and sine controls vertical, then this means the directrix must be below the pole and must be parallel to the polar axis. Let's now see if we can draw a sketch of what we think it would look like. We'll start again with our polar axis on top of a rectangular coordinate system. Remember that one of the focal points is always going to be located at the pole. In this case, because we have sine and because we have a negative here and the focal parameter is positive, we know the directrix line must be below the pole and at a distance of 8. If I count out along these circles, I know that this one is -10, which must mean this one is 8. That means my directrix line is down here. Now I know that I have an ellipse, so the question is, how can I draw the ellipse? Where can I find the different parts of the ellipse? Now that we know that the directrix line is here and the focal point is here, this must mean that because we have a sign in it, that the ellipse is oriented vertically, meaning that it is longer in the y direction than it is wide in the horizontal or x direction. How then can I find the endpoints of the major axis? Since the focal point is on the 180-degree line between 3 pi over 2 and pi over 2, then the angles pi over 2 and 3 pi over 2 must be the endpoints of that major axis. That means that we can plug them into the equation for r to find the endpoints of the major axis. Let's find what the value is when we use, for example, pi over 2 for the angle theta. R at pi over 2 would become 8 divided by 2 minus the sine of pi over 2, which is of course 1. This gives me a length of 8. That means that on this particular polar axis, that I need to go out to the 8th concentric circle, 7, 8, and put a ball there to represent the endpoint of the major axis in that direction. Now we'll use the angle in the opposite direction of 3 pi over 2. Plugging in 3 pi over 2 into the radius equation would give me a -1 in the denominator for the sine of 3 pi over 2. That would give me instead 2 minus a -1, which would be +1, or 8 divided by 3. That would be the same as 2 2/3. Coming out to the graph, we would go to the second concentric circle and 2/3 of the way to the third. And that would be the location of the other end of the major axis of this ellipse. That would be there. That would give us these two values to represent the endpoints of the major axis. This also then can help me figure out where the center of the ellipse must be, because it's got to be, you got it, halfway in between. Well, where's the center? If I know, for example, that I'm 8/3 in the down direction and I'm 8 in the up direction, then the entire major axis must be 8 plus 8/3. If I then take half of that, that would be the location of the center. Half of 8 plus 8/3. That would be 24/3 plus 8/3, which would be 32/3. And half of 32/3 is 16/3. That would say that halfway in between, or at 16/3, which is 5 1/3 between them, I should find the center of the ellipse. It'll be easier to go from the one that's on the actual concentric circle at 8. We're going to go get down now, and we'll mark this one with a pink color. Coming down, I'll come down 1, 2, 3, 4, 5, and a little bit more, and put an X, for X marks the center. That is the center of our ellipse. From this point, again, I would have moved up 1/3 and then 5. 1, 2, 3, 4, and yes, it does put me in precisely the right location. Once I know that, then I can compute the length of half of that major axis, which is A. This would be the distance between the 8 and this, which of course is simply the 16/3. This represents A. Now that I know A, I can compute C. C is the distance from the focus, of course, to the center. from the focus to the center would be a distance of 2 2/3. That means that the value of C is equal to 2 2/3, or if you want to write it in terms of an improper fraction, 8/3. Once we know those two values, we can compute the minor axis B. Remember that for an ellipse, A is longer than C. That will give us the relationship of B from the equation B squared is equal to A squared minus C squared. This is the relationship that you learned about in Calculus 1. Since we know that B squared is A squared minus C squared, and I know that A is 16/3, that will give me 256 divided by 9 minus C squared, which is 64 divided by 9. If you do the math, you should eventually end up with 192 divided by 9 for B squared. That makes B equal to 8 square roots of 3 divided by 3, or approximately 4.6. Returning again to our graph, this means that I can return to the center here at 2 2/3 and move out left and right approximately 4.5 squares. That will put me right about here on the right, and let me mark it with red, and about here on the left, again marked in red. This then would become my ellipse. It's not a great picture, but then I'm not a great artist. Let's take a look and see how well we did when we compare it to what Desmos has produced for the same equation. Looking at the equation now for Desmos, we can see that our picture is in fact pretty close. It looks pretty good. It's not too bad. Now, I'm not expecting perfection, and I'm not expecting perfectly drawn conic sections. I am expecting you to be able to take the equation, to put it in the correct form, to tell me if it's an ellipse, a hyperbola, or a parabola, and to find the focal parameters, and then to use some of that information to be able to graph it simply. Let's take a look at another example. It's the same problem. Let's get this equation for r in the correct form for graphing in the polar coordinate system. That means the 2 has to change. It's got to be a 1. First thing we're going to do, multiply by 1/2 divided by 1/2. This gives us r equals 5/2 divided by 1 plus 1/2 sine of theta. Now that I have a 1 in the denominator, I look at the absolute value of the coefficient of the trig function in the denominator. That gives me the eccentricity of 1/2, which is less than 1, which tells me that this is, again, an ellipse. Then I look at the numerator. It's 5/2. That means the eccentricity times the focal parameter has to be 5/2. I know the eccentricity, it's a half. That means if I multiply both sides by 2, I should be able to solve for the focal parameter. Solving for the focal parameter gives me 5. Since the focal parameter is positive and I have a positive in the denominator, I know that the closest directrix line will be located in the positive direction with respect to the pole. Since the equation involves sine, which is a vertical controlling function, then that means the directrix will be above the pole and parallel to the polar axis. Let's see if we can now figure out where that might be. We'll reproduce the graph again and we'll start graphing. Here's the graph that we can see here. We know the focus is located at the pole. We know that the focal parameter is 5, and because both that and the sign in the denominator are positive, and it is sine, that it must be above the pole and parallel to the polar axis off in the positive x direction. 5 would put it here. Since it is an ellipse and it is sine, it must be running vertically, which means it is longer in the y direction than it is in the x direction. Now I can find the endpoints of the major axis by locating it along this pi over 2 and 3 pi over 2 line. When I calculate the value of the equation given here at pi over 2, what do I get? I get that r evaluated at pi over 2 is equal to 5/3. When I evaluate the radius at 3 pi over 2, since sine of 3 pi over 2 is -1, I get 5. Now I'm going to come down and I'm going to draw it with those in mind. That means that when I'm coming from here and I'm going down in the 3 pi over 2 direction, I should be down here at 5. When I am in the pi over 2 direction, then I am only coming up to 5/3, which is 1 2/3, or about here. Once I have that in line, then I know how far the major axis is by adding those two together. When I add the two together, I can get that the major axis has to have a length equal to 5 plus 5/3, or 15/3 plus 5/3, which is 20/3, or 6 2/3 long. If I take half of the length of the major axis, that will be A. Since A is equal to half of the major axis, that means it must be 10/3, or 3 1/3. Since it's 3 1/3, then I should be able to count from one of the endpoints to locate it. I will go from the one at the bottom since it's directly on one of the concentric circles. Counting up 1, 2, 3, and 1/3 more, I'll again put an X to mark the spot. From there, if I were to count up again another 3 1/3, the third would put me at the 2/3 mark, and then 1, 2, 3 would put me right on top of the other endpoint of the major axis. Once I know where that is, then I can compute the value of C. From there to the focal point, how long is that distance? Based on the location of the center and the focal point, C must be at 1 2/3, which is equal to, of course, 5/3. Once I have A and C, and I know that it's an ellipse, since A is longer than C for an ellipse, then I can find the length of the minor axis by computing B squared, which is A squared minus C squared. This means that I will come up with the value of 100/9 minus 25/9, which is 75/9. When I compute the value of B, this would give me 5 square roots of 3 divided by 3. Now let's find out on the calculator about how much that is. That's roughly 2.9. Return to the center of the ellipse and move just less than 3 squares to the right and just less than 3 squares to the left. 1, 2, 3-ish. This will give us our ellipse. Now let's take a look at the graph produced by Desmos and see how close we got. Again, we did fairly well. You'll notice, of course, that our value down here at 5 is spot on, and that our value up here is also spot on. This looks fairly close to what we were able to hand draw. Let's take a look at one more example, and then I'll give you a series of examples with solutions, though I won't work them out here in this video. In example 4, we're asked to again take the conic section equation in polar coordinates and put it in the correct polar form for graphing. That means the constant in the denominator must be a 1 for that constant term. It is not a 1, so instead I'm going to multiply by either -1 divided by -1, or you could do 1 over -1 over 1 over -1. Either way will, of course, work. This leads to r being -5 divided by the quantity 1 minus 2 sine theta. Notice that fixing the constant term in the denominator changed the sign of both the numerator and the other term. That's going to affect the value of the focal parameter. In this case, when we're done, we'll see that the absolute value of the coefficient of the trig function is 2. Since that's the eccentricity and it's greater than 1, then we must have, in fact, a hyperbola. Since I have a hyperbola, this means that I'll have 2 branches. When I have that done, then I look at the numerator, which gives me the product of the eccentricity and the focal parameter p. E times p is a -5. I know the eccentricity is 2, and that means that the focal parameter must be -5/2. In this case, both the focal parameter and the sign between the two terms in the denominator are negative. Because they're both negative, that tells me the location of the directrix line with respect to the pole will be in the positive direction. And since the trig function is sine, which is vertical, that means that the directrix line will be above the pole, running parallel to the polar axis. Now that we know that information, let's try to graph it. So far, I know that the focal point will be located at the pole, and that the directrix line has to be above the pole because there was a negative in the denominator and the focal point were negative, and that's a double negative. It will be a location of 5/2 units away from the focal point, or 2.5 above. That would put it right about there. That's the first directrix line. There are 2 directrix lines. You'll notice I did not draw them on the previous graphs, though of course I could have by computing the location of the other focal point and then measuring its focal parameter distance away from that focal point. In this case, what we're trying to find is the graph of the hyperbola. Remember that the back of the hyperbola will be turned towards the directrix lines. That means that one branch of the hyperbola must be curving this direction and this direction. Again, it is opening vertically because we have sine involved. Now let's see if we can figure out where it's got to be. Since we have sine involved and it's opening up and opening down, that must mean that the major vertices are once again along this pi/2 to 3π/2 line. Let's compute what those are now by plugging the values of pi/2 and 3π/2 in for r. That gives me 5 divided by -1 plus 2 when I use pi/2, which becomes 5/1 or 5. When I use 3π/2 instead, I get -1 or -1 minus 2, which will give me 5/3 or -5/3. Now, this is a little bit unusual. What does that mean, in fact, for this to give me a -5/3? It means what it always means. It means that you begin in the 3π/2 direction, but because the radius is negative, you will actually shoot out again, yes, in the pi/2 direction. That means they're both in the pi/2 direction. The first one, when pi over 2 is used for the angle, gives us a radius of 5. That would be located here for the vertex of the upward opening part. Then when we used 3 pi over 2 for the angle, we get negative 5/3, which again puts us out along the pi over 2 line, but at 1 2/3, which is here. Now we need to figure out where the center is. The center has to be halfway between these. One is at 5 and one is at 5/3. In order to find the center, we can simply find the midpoint. Add 5 plus 5/3 and divide by 2. That would be 15/3 plus 5/3, which is 20/3, divided by 2, which is at 10/3, or 3 1/3. That means that the center has to be located 3 1/3 units from the origin on the rectangular system. 1, 2, 3 1/3. You can see that that is halfway in between the two major vertices for the hyperbola. Now that we know that this is where the vertices are, how can we locate where the rest of it is? Again, we need to find C, the distance from the center to the focal point. But we have the distance from the center to the focal point. One of the focal points is here at the pole. Since the center is at 3 1/3, that happens to also be C. That means that 10/3 is the value of C. Remember that on the hyperbola, C is greater than A, so to compute the minor axis, we'll need to compute B squared as C squared minus A squared instead. In this case, we need to find A. A is from the center to one of these major vertices. How far is that? The distance between the center at 3 1/3 and the major vertices, one of which is at 5, is 1 2/3, or A is equal to 5/3, or 1 2/3, depending on which version you prefer. Plugging that into the equation for B, I get then that C squared, which is 10/3 quantity squared, is 100 over 9, minus the 25 over 9 that I get from A squared. Again, we've done this one before. This gives me 75 over 9, which is, of course, 5 square roots of 3 divided by 3 when I solve for B. I believe we found last time that that value was about 2.9. Just less than 3. Now, how can I use that to draw the rest of the hyperbola? Again, come to the center and go out from the center about 2.9 to the left and to the right. 1, 2, 3, put a little mark. 1, 2, 3, put a little mark. Now you need to draw a box. It'll be easier if we make the sides of the box really thick so that we can see them. The box has to go through the major vertices and through the B value. This is going to come across then and hit through those points. Now we will draw the lines that go through the corners of the box and the center of the hyperbola. These are your asymptote lines. Again, I'm not expecting perfection. Good is good enough. Now come back to the major vertices and draw hyperbolas that hug along those asymptote lines as it opens up and down. That's the best rendition I can do for this hyperbola, but I expect you can do better. Let's take a look now at what Desmos did and see how close I got. Here's Desmos's picture. It's close. It's very close. There are several more examples that I would like to show you the solutions for so that you can practice at home, since there are really no examples in the book for you to follow along. So I will give you the problem and then I'll show you the picture from Desmos so you know what the solution should look like. Let's take a look at example 5 now. Here's example 5. Don't forget step 1, that 2 has to be made into a 1. If I make it into a 1, then I'm dividing by 2 in the numerator and denominator. That will make this a 3, which means it must also be a hyperbola. If that's a 3, then the focal distance will be a 1/2, in which case, because that's negative and the focal parameter is positive, I know that it will be located below the pole. In this case, since it's sine, it will be parallel to the polar axis. I'm expecting a hyperbola with the directrix running parallel to the polar axis, but below it. Let's look at the picture and see how I did. Bingo, not too shabby. You can see that the directrix lines must be below the pole and that it is opening up and down. What about example 6? In example 6, I have -4 for the constant term in the denominator. Big problem. I've got to multiply by 1 over -4 over 1 over -4. That will make the numerator negative and make the second term negative. This will become 3/4 for the absolute value of the trig function's coefficient, which means the eccentricity is less than 1. This must be an ellipse. But because this is negative and the numerator is negative and it's sine, I'm expecting the directrix line to in fact be above the pole. I'm expecting it to be an ellipse running vertically with the directrix above the pole. Let's see how we did. Bingo! Looks good. You'll see that the directrix line, the closest one to the focal point here, is going to be above the pole. Yes, there is another directrix line which would be down here. We could find it by locating the length of the major axis, computing A and then C, and then locating the other focal point here, then using the focal parameter to find the distance to the other directrix line. I won't require you to do this. Now let's take a look at another example. Here's example 7. Similar to the last problem, we'll have to divide by -4. That will make the numerator -3/4 and the coefficient of cosine also -3/4. That means the eccentricity tells me that it's going to be an ellipse, but this time I have cosine, so it will be running horizontally. Because I'll have a negative in between and the numerator is negative, I'm expecting the directrix line to be in the positive location to the right of the pole. Let's look and see if that's what we got in the picture. Here's the focal point, and the directrix line closest to it would be to the right of the pole. You can see that this picture is an ellipse which is running horizontally. Let's look at another example. This is example 8. In example 8, I need to divide by 1 over -2 divided by 1 over -2. That will give me another fraction up here of -1/4 and make the coefficient of cosine -3/2. That means that the eccentricity is 3/2, so it must be a hyperbola. However, this will be negative and this will be negative, and that means that again, I will expect to find the directrix line to the right of the pole. It should be running horizontally, but because it's a hyperbola, that means it opens left and right. Let's take a look at the graph and see how our prediction did. Here is again the focus at the pole. And you can see that the directrix line closest to it is to the right. In fact, because it's a hyperbola, The directrix lines are both to the right. Let's take a look at another example. In example 9, we will have to multiply by 1 over negative 3 over 1 over negative 3 to make this constant term become a positive 1. That makes the numerator negative 5/3, and the denominator will make this minus 1 cosine of theta. Because the coefficient of cosine will become an absolute value of 1, I know this must be a parabola. Then I will have a negative in between and a negative in the numerator, which tells me I can expect to find the cosine, or rather the directrix, on the positive side of the pole. Because it's cosine, I know that the parabola must be horizontally oriented. Since I'm expecting the directrix to be on the right side of the pole, then that would mean that it must be opening to the left. Let's take a look at the picture and see how we did. We are on a roll. I think we've got it. This means that the directrix will be here on the right and the focus is here. Cosine is making it open in a horizontal direction, and because the directrix is on the right, the parabola must open to the left. Let's take a look at one last example. Here's example 10. In example 10, I again will need to multiply by 1 over 3 over 1 over 3 to force the constant term in the denominator to be a positive 1. That will not change the sign of the numerator or the second term in the denominator. It will, however, change the numbers. It will become negative 2 in the numerator and negative 2/3 as the coefficient of cosine. Eccentricity is the absolute value of that, which means it's 2/3, so I have an ellipse. Because this is negative and the numerator is negative, I'll expect to find the directrix on the positive side of the pole. Because I'm looking at cosine, I know that this has to be an ellipse which is running horizontally. I will expect then to find the directrix on the right side of the pole. Let's take a look at the picture and see how we did. Here is the focus that is located at the pole. The closest directrix line would be to the right. You can see again that the ellipse is running horizontally. I hope that you can see that in this sense, the polar coordinate system is much simpler for representing conic sections, since the form of the equation is very similar to all of them, and a great deal simpler than what it is in the rectangular coordinate system. This ends this video.